a simple application of it, and it's got plenty of applications. And you guys are getting into mechanical engineering or civil engineering, we'll see tons of applications. Everything is based on these little examples that we're doing. So we got this toy dart gun, and it's gonna shoot darts. Basically, that's what it does. All right. So here's the unstretched position. All right, and then we will just compress the spring in this direction. So this is the compressed spring. So compression is going to be 6 centimeters. And this is the stretch position. This is the mass in terms of kilograms. And this is the stiffness of the spring. So what's the speed of the dart? What's the speed of the dart? Initial speed is going to be 0. So what's the final speed? As it's exiting the toy gun. All right. So how do you do a problem like this? Number one, okay, so if you're making assumptions, you're making assumptions in the first step, not in the middle of a solution. All right. Assumption is we're ignoring friction. That's an assumption. Okay, because our solutions will be sensitive to initial assumptions that we're making. So as soon as I say, hey, I'm going to ignore friction, which means that I'm going for an estimate at this point. So mechanical energy is constant, if that's the case. So mechanical energy is a combination of kinetic and potential energies. So when the conservative force, the restoring force is at work, the mechanical energy is constant, ignoring friction. All right, so kinetic energy is this. So that's going to be our kinetic energy right there. We got an expression for the potential energy. Okay, so potential energy expression is loaded. It says potential energy. One of them is the gravitational potential energy. The second one is the elastic potential energy. Obviously, in this case, we'll be interested in the elastic potential energy, right? So that's what we need to use. All right, boom, boom, boom. Okay, so this problem is straightforward. All right, so if we have any zeros, plug in the zeros. All right, so what do we have? Unstretched position is going to be 0, so that term, this one is going to be 0. Initial speed is going to be 0, so that term is going to be 0. So initial speed is 0, so that's going to go. And the final position, stretch length is going to be 0, so that term goes away, so it's this one. Okay, so the rest is algebra. Get rid of 2's and get rid of m's. Boom, boom, boom. And then I drop the term there, so I'll redo it. Finish it up. And then stop at this point. Check to see if this makes sense. Right, so the more you compress the string, the faster the dart is going to move, so that makes sense. Stiffer the spring is, the faster it's going to move, so that makes sense. More massive the dart is, the slower it's going to move, so that makes sense. Right, so get the answer in terms of meters per second converted to miles per hour. So it'll give you 7 miles per hour. With surface friction, it's probably going to be 6.5, so that's reasonable. Okay, so this is a quick example of how nicely the concept works.
June 20th, 1999, Santa Barbara, California. Stacy is among 10 top female pole vaulters competing at the 4th annual Comes Up Short on her first 2 tries.
And on my last attempt at the record height, I said, you know, I got to give it my all right here. I got to put a really good vault together.
On her last try, Stacy clears the bar and vaults into the record books.
It was the greatest feeling going over the bar and coming down and landing on the mat.
June 20th, 19...
Height, I said, you know, I got to give it my all right here. I got to put a really good vault together.
But she comes up short. Stacy has 3 chances to set a record and claim the cash.
All right, so she's trying to clear a height, which is 15 feet, right?
15 feet and 3/4 inches.
All right, give and take 15 feet. So how fast does she have to run in order to clear this height?
Stacy has 3 chances to set a record.
All right, so what does that mean? So now the setup is this complicated process at this point. How do you set something like this up? All right, so how does this setup take place? All right, so which means that her kinetic energy
claim the cash
has to get converted into the elastic potential energy of the pole. And then elastic potential energy of the pole is going to get converted into her potential energy.
But she comes up short.
So let's go back again. So the faster she runs,
Stacy has 3 chances to set a record and claim the cash.
the more she's going to be able to bend this. So which means that she ends up applying a tremendous amount of force on it and is able to bend it. So which means that the energy is going to get transferred into the pole that she's bending. And then the restoring force kicks in at that point. And then restoring force is going to apply a force on her. All right, so which means that the energy is going to get transferred to her. And then that becomes her gravitational potential. So with that in mind, now you can actually solve that problem. So the initial form of energy is going to be kinetic energy, right? Now what's happening is that kinetic energy is going to go into the deformation potential energy, elastic potential energy of the pole, and the elastic potential energy of the pole is going to become her gravitational potential energy. All right, so restoring force is a conservative force, gravity is a conservative force. So when the restoring force kicks in, the potential energy of the pole is going to turn into her potential energy. Anyway, so a bunch of assumptions here that we need to focus on. So how fast does she have to run in order to clear the site? So that's what we're interested in. All right. She's trying to clear the site that's going to be 15 feet high. We're making the assumption that the gravity is the only force acting. Let's start from the restoring force that we got. So which means that we're ignoring friction in this case. All right. So because of the fact that you got two different conservative forces at play, so the work done against the pole is going to go into the potential energy of the pole. And the pole is going to do work on her, so that potential energy is going to get transferred to her. It's going to become her. It's going to become her gravitational potential energy. When you're dealing with conservative forces, the path of motion doesn't matter. The only thing you have to worry about is the initial and the end points of motion. The initial point of the motion, the mechanical energy is going to be all kinetic. End point, the mechanical energy is going to be all potential. All right, so the initial form of mechanical energy is kinetic energy. The final form of mechanical energy is going to be all potential. So that's what it means. All right, so mechanical energy is going to remain constant once again because gravity is a conservative force, or is the restoring force. And then we're only interested in the initial and the final points of motion. All right, so kinetic energy is going to be 1/2 mv squared. Potential energy is going to be mg times y. So let's solve for the initial speed. So get rid of the masses, multiply both sides by 2, and we are done. Okay, algebraically, this one is straightforward, but notice that 90% of the work was done conceptually. So plug the numbers in, and then you end up getting a number. It's going to be about 10 meters per second, 21.5 miles per hour. Okay, we're not done yet. The next question is, does this number make sense? Okay, so only thing we know so far is she literally cleared that height. All right, so she successfully cleared that height. It was set to 15 feet and 3/4, and for her to be able to clear this height, obviously she was above 15 feet. It was about 16 feet and even probably slightly higher than that. According to our computation, she had to be running at 21.5 miles per hour just to clear the 15 feet high. So if she's at 16 feet, that's about 22 miles per hour. So what's she running that fast?
A human being goes
It's 22 miles per hour.
without machine power.
Is it sprinter speed? These are the guys who run that fast. Okay, in fact, you're looking at Michael Johnson. It was over 23 miles per hour. So what does it mean? What does that mean? What that means is there's no way she was running at 22 miles per hour. There's no way. You can't run that fast with a pole in your hand. If she could run that fast with a pole in her hand, without the pole, she would be running about 24, 25 miles per hour. So it's out of the question. Olympic sprinters can run fairly fast. They can go up to about 19 miles per hour. Okay, so which means that there are some assumptions which are not correct. Right, so I always say your quality of your solution is sensitive to the quality of your assumptions. Usually, there are some bad assumptions here. Okay, biggest assumption that I made, worst assumption that I made, I took the initial point, initial height with respect to the ground. I made it 0. Okay, that's a big no-no because I'm just measuring everything with respect to this person's feet. You can't do that. Everything has to be measured with respect to center of mass. The idea is to get your center of mass over the hurdle. If your center of mass is not getting over the hurdle, I don't care which position you turn, you're not going to be able to clear that height. So you got to follow the center of mass. And so you want your center of mass to be as high as possible with respect to the ground. That's the reason why these guys tend to be fairly tall. All right. So you want to actually close the gap between your center of mass and the height that you're trying to clear. So the taller, the better. That's what the guys go for. She's actually fairly tall. She's probably 6 feet. All right. So her center of mass is at least 3 feet off the ground. If that's the case, her speed is not going to be 22 miles per hour. When you do the computations, you're probably going to end up getting 18 or 19 miles per hour. That's still way too fast. For Olympic athletes, yeah, they can go up to 18 or 19 miles per hour. This is a beach championship. She's not an Olympic athlete. She's fast, but she's not that fast. Reasonably speaking, she was probably going at 14 to 15 miles per hour. That's still damn fast. So she had enough kinetic energy to get her center mass up to this point. Now follow the center mass. Her center mass is located somewhere. All right, so let's just back out of it. Let's back out of it. Okay, so now it's almost a full stretch. Notice where her center of mass is. Her center of mass is here. Her center of mass is about 1 foot or 2 feet below the mark. All right, so all the energy that she was able to store into the pole was all the energy that she was able to take back. So her kinetic energy just provided a height came about because of the conservation of mechanical energy. It still falls short of the target. Okay, so the question is, for her to be able to get over this target, where does she get the extra energy from? Guys, where does she get extra energy from? She gets it from her muscles, right? Okay, she's extremely coordinated. She's extremely strong. Look at the arms. So which means that she's utilizing propulsive force. She's generating a propulsive force using her muscles. And the muscles are getting the energy from chemical potential energy that turns into heat and then turns into kinetic energy. So the extra energy comes from there. So during pole vaulting, your kinetic energy is only going to give you so much height. So your kinetic energy is going to get converted into potential energy of the pole. Potential energy of the pole is going to get converted into your gravitational potential energy. And you will still fall short. You will never have enough speed to get over this height on your own. The rest of the energy has to come from the body. And that's exactly what happens. force. So the extra energy comes from muscles, and muscles usually utilize the chemical potential energy. So that turns into heat and whatnot. And then the person gets over the hurdle.
The referee says take
All right, so the next topic of discussion is power.
the strain, and what a strain it's going to be. Those starting blocks again hammered into the ground. That gives the competitors a firm grip. It's almost like a rowing action, and good rhythm is going to be so important. Look at that effort in his face. His legs will be burning. His arms are surely hurting now. The clock will stop any moment now, 42.36, and that is a strong target. He nods, he's ready, and now the effort. Every time this man steps up to take part in an event, the crowd go absolutely wild. This clapping won't do him any harm at all. It's setting up a rhythm, and that's what he needs to go for a good time. Coming up to 30 seconds, it certainly is going to be very fast. 34.34, that has to be the winning performance. The clock will stop any moment now, 42.36. And
All right, so if I were to ask you which guy is more powerful,
that is a strong lead, the winning
you got the answer, right? All right, so it's the same airplane, the same distance.
performance.
The amount of work that both of them are doing is, I mean, force times displacement. It's a combination of force and
The clock will
displacement.
stop any moment now,
Except one guy does it in a shorter amount of time.
42.36.
So if I were to ask you which guy is stronger,
And that is a strong target, 34.4.
the first guy takes like, what is it, 45 seconds. The second guy is going to take about 35 seconds.
That has to be the
All right, so the second guy was able to do the same amount of work faster, so which means that he's going to be more powerful.
winning performance.
All right, so power means a couple of things, all right, in terms of physics. All right, number one, power is how fast the work is done. All right, so work is a passive transferring energy, so which means that how fast the energy is transferred. All right, and when you transfer energy, obviously you could also be converting energy, so how fast the energy is converted. All right, so that's what it means. How fast the work is done, how fast the energy is transferred, and how fast the energy is converted. All right, so mathematically, how fast the work is done is the rate at which the work is done, so it's work over time, how fast the work is done. Okay, work is a passive transferring energy, so it's the amount of energy that you transfer. So W becomes delta E. So how fast the energy is transferred, so that becomes the second statement. And then we end up getting something interesting out of this. But also, work is a combination of force, cause, and displacement. So there's force and there's displacement, right? So when you do a substitution into this expression, notice that there's displacement over time. Little expression means speed, okay? So which means that how fast force is transferred, in essence. That's kind of weird. All right, so the last statement is a combination of force and the speed of that force. All right, so how fast the force is transferred is also going to be your power. All right, so from the formula sheet, we got a bunch of expressions. So power is how fast the work is done, how fast the energy is transferred, so the transferred energy can appear in the form of kinetic energy. Or if the power is how fast the work is done by gravity, so gravity diminishes the potential energy. And power also means how fast the force is transferred. Okay, guys, you see these W's or omegas? It's not intentional. All right, so when I was transferring stuff and changing format for whatever the reason, the word ended up putting those W's in. I just didn't know how to delete them. So just ignore that. They're in the formula sheet unintentionally. Okay, so P here means power. It's going to be expressed in terms of W. W is going to be watts. All right, so here, that's the reason why I use brackets. So here, W is not the same as work. So this is your work. So it's going to be in terms of joules. T is going to be time. So work is in terms of joules. So it's going to be joules per second, which is otherwise known as watts. All right, so this W means watts. In the United States, we use horsepower. So 1 horsepower is going to be 746 watts. Okay, so that's everything you need to know about power. So power is how fast the work is done, how fast the energy is transferred, how fast the energy is converted. Proper unit is watts. We use horsepower in the United States. All right, speaking of horsepower, obviously the common way of expressing power in the United States is horsepower when it comes to cars. Right? Expensive cars, the cars can have really amazing accelerations like 0 to 60 or whatever. You're looking at anything over 200 horsepower usually. Right? My Ford Tempo, its horsepower was about 120, but it didn't drive like all the horses were pulling in the same direction though.